Hey team, it's me, Andrew Voss. Today we're watching Falcon 9 re-entry and landing videos and talking about the fundamental first physics behind Falcon 9 landings. What forces are being applied? Which direction is the Falcon 9 headed in? Which direction are those forces applied? And then what is the net acceleration on the Falcon 9 at that point? So we'll watch this sped up video of launch and landing on board the Falcon 9 to begin our study. Here's the ascent phase, sped up, leaving Cape Canaveral. Here, Falcon 9 is leaving the atmosphere. Now the Falcon 9 first stage has separated from the rest of the rocket and will be beginning its return journey to land. At this point, it's far outside of the atmosphere. It has substantially reduced weight from liftoff after burning through all its fuel, or nearly all its fuel. And the only forces really acting on it are the weight, because there's no atmosphere to produce a drag force and the engines are off. So it's just doing some maneuvering to reposition itself to return to the launch site. What's about to happen is called the boost back burn. And here, a few engines will turn on with 190,000 pounds of force each to boost back the rocket towards the launch site and put it back on its trajectory while still in free fall towards Earth. So here's the boost back burn, boosting the rocket quickly back towards Cape Canaveral, the landing site. So now the Falcon 9 is still in the atmosphere. The grid fins are deployed to prepare for atmospheric reentry and to control the drag forces in a way that steers the rocket. The little puffs or farts of air are thrust from the ACS system, which is just used to maneuver and rotate the rocket around in space with tiny amounts of force. This next major event that's happening is the entry to the atmosphere. So at this point, the air density is increasing to the point where there is a real and large drag force in the atmosphere. As the Falcon 9 continues to descend back towards Earth, the air density and thus the drag force will get larger and larger. Now remember, the Falcon 9 velocity here is very high. And so with drag being proportional to your velocity squared, the drag forces when you're going fast through the atmosphere will rack up quick, and you'll be able to actually see those in the video. To enter the atmosphere, Falcon 9 does a re-entry burn, turning on a few of its engines again to slow down the rocket to minimize those drag forces upon hitting the atmosphere hard. Falcon 9 can hit the atmosphere so hard that it's almost like cannonballing into a pool. Hitting that atmosphere produces a huge amount of force, and you don't want to belly flop or it could tear the rocket apart. See, these here are the engines on, denoting the entry into the atmosphere. That is the completion of the reentry burn, but now the aerodynamic forces and the air density will get higher and higher as the altitude gets lower. You can visualize them now, coming through the grid fins. This phase here of coasting through the atmosphere with the engines off, followed by landing burn, has some very interesting dynamics that we'll dig into later on in the session. Now the engines have turned on for landing burn. The landing burn continues until the Falcon 9 touches down on the pad. It is not all of the engines. Usually in a case like this, it's just one of them, producing a throttled down version of the full 190,000 pounds of thrust of a Merlin engine. But occasionally you can do a 3-engine landing burn that produces more aggressive accelerations and forces on the rocket. Those landing burns are always downrange on the drone ship and are much shorter and start at a lower altitude. The 3-engine landing burn is considered more risky and aggressive, but it preserves the performance of the launch better by requiring less fuel to land the rocket. The Falcon has landed. All right, so here on this infographic, you can see the major Falcon 9 events for landing in their various sections here, starting with this flip maneuver, which we saw where the cold gas thrusters flip the vehicle around before the boost back burn as it coasts high above the Earth's atmosphere. Then it comes in, deploys the grid fins, lights up the engines for rocket re-entry, controls itself down, and does the final landing burn, touching down on the pad. Let's look at the physics right before boost back burn starts. I'll start by drawing that the direction of motion of the rocket is moving this way, just coasting with the velocity off towards the right. Now I'll change the color and draw the forces acting on the Falcon 9. In this example, the only force acting on the Falcon 9 is the weight, which is pulling it back down towards Earth. There's no drag because it's way out of the atmosphere and the engines are off. So the weight acts in the downward direction, pulling it down to Earth. So the sum of the forces in this direction then mean that the vehicle is accelerating downwards at 1g. 1 gravity is the direction of the acceleration and the value. So 9.81 meters per second squared, or 1g. Now at boost back burn, the direction of motion is still towards the right and we're still out of the atmosphere, but a new force is added to the equation. We still have the weight acting downwards on the rocket, pulling it towards the Earth, but we also have a thrust force, which is equal to 190,000 pounds, which is the amount of force one Merlin engine puts out, and that's multiplied by the number of engines that fire in the boost back burn. So in this case, the vehicle acceleration is in the direction of the sum of the forces, which will be this way. At re-entry burn startup, the situation's similar, but it's about to change with the addition of drag force as the rocket enters the atmosphere. Here's the direction of motion in red. The forces on the rocket are the weight and the thrust. In this situation, the thrust is substantially greater than the weight. That means that the vehicle accelerates in the direction of the thrust, or the upward direction. So in this instance, the acceleration directly opposes the direction of motion, and this would be called a deceleration. So the rocket is actually slowing down despite the fact that it's accelerating. This is similar to being in a car and braking heavily. You feel pinned against the back of your seat, but your body is accelerating despite the fact that you're slowing down. Now, after the engines shut off on the reentry burn, there's still a large amount of force on the rocket from drag. The situation is similar, but the drag force actually continues to increase. So the direction of motion here is downwards. The forces acting on the rocket now are just the weight acting downwards towards Earth and the drag, which always directly opposes the direction of motion. Now, in this situation, the drag is actually greater than the weight, meaning that the rocket is decelerating and slowing down on its approach to Earth. Despite the fact that the engines are not even on, the drag force is so high from how fast the rocket's moving that it's slowing down the rocket, similar to the belly flopper jumping into the pool, doing a cannonball or smacking their back. Now, finally, we move on to landing burn start. Here we have a video of the rocket coming in for a landing back on Earth. Here it's already through the re-entry phase and is coming up on landing burn startup.
Stage 1 is transonic.
Stage 1 is past the speed of sound.
So here it is still decelerating, slowing down just as we've drawn before. You can see that the direction of motion is clearly this way, and there are still multiple forces acting on the rocket, most notably the weight pulling it downwards, and the drag force, which opposes the direction of motion and is greater than the weight, again, in this situation, because this atmosphere is so dense and the rocket is moving so fast or at such a high velocity. That means that there's still a net deceleration on the rocket in this direction, where it's accelerating towards outer space, despite the fact that its motion is back down towards the Earth.
It's now subsonic.
Now let's see what happens when the engines start up.
Landing burn underway.
All right, now the center Merlin engine has fired up at 190,000 pounds of thrust and changed our forces equation. We have the direction of motion, the rocket's moving here. That means again that the drag force is directly contrary to that. So let's draw our drag force here. The drag force is now reducing because the vehicle velocity is getting slower. But there's a substantial additional force here, 190,000 pounds from the Merlin thrust. And still, the weight is pulling the rocket down towards the Earth. So in this situation, the thrust plus the drag minus the weight is a positive number, meaning that the thrust and the drag are greater than the weight. So the vehicle, again, is still decelerating. This process of decelerating and slowing down through Earth's atmospheric reentry is the process of doing a Hoverslam landing, where Falcon 9 can get to a touchdown velocity of 0 on the ground. That's like trying to get your car braked and exactly stopped right as you hit a red light, exactly on the line where you would cross into the intersection. Well, I hope this example has helped you understand the dynamic changing forces during rocket flight. As you can see, the forces are always changing, and thus the acceleration on the rocket is always changing in a way that finally brings the rocket down to that graceful touchdown landing, whether it's on the drone ship or back at Cape Canaveral. The imbalanced forces are almost always during the landing, causing a deceleration or opposing the motion and velocity of the rocket. This process is so dynamic that the rocket nearly never finds itself in a pure terminal velocity state where the velocity is not changing at all. As it hits the atmosphere, it begins to slow down rapidly, whether the engines are on or off. The engines just increase the speed at which the rocket slows down. I hope you've enjoyed and continue to learn more from the Falcon 9 and this program.